So before I get started, I just have to share that the very first ISAC talk I ever gave, which is my first real professional talk where I actually traveled somewhere, I was put in the very last session of the conference. And I had this depressing scene of watching everybody show up on the last day with their suitcases. And as the day progressed, people would leave for their flights and everything like that. And I thought that I would be immune to this in a virtual conference, but instead I think people have just started their weekend plans early. But that's okay. I really appreciate the people that are here, especially since many of you are in Europe, which means that it's late on a Friday night and you're probably desperate to go. So I'm sorry to stand between you and whatever fabulous plans you have. All right, so let's see if I can get this to go. Here we go. All right, so the context of this talk is SAT solving for nonlinear polynomial constraints with reals, right? So the QFNRI theory from SMT-lib. And it does involve cylindrical algebraic decomposition, which people have already talked about, which means maybe I don't have to. So of course, CAD provides a tool that can in principle solve the satisfiability problem, but in practice, it's problematic. Oops. So what I want to do in this talk is I want to compare and contrast three algorithms that use SMT ideas to sort of blow up the usual CAD process. And they reassemble the pieces into something more efficient. So hopefully we'll learn some interesting things about how these algorithms work, and it might spur people to have clever ideas in the future, which I think would be great. So the first algorithm that I want to talk about is the Nlsat algorithm of Jovanovic and Demora from 2012. So this was a very inspiring paper for me. It introduced me to the SMT world, really, and it gave me lots of ideas. And I think it was also probably inspiring for a lot of people to see these interesting connections between computer algebra and the SMT world. The other paper, second paper I want to talk about is the paper from this year, came out at least this year, on cylindrical algebraic coverings, which inspired me to want to give this talk, right? Because I really want to understand the differences between these two approaches and how they compare with non-uniform cylindrical algebraic decomposition, which is something that I came up with in 2015, very much inspired by Nlsat. So CAD from 40,000 feet, just so that we're on the same page about what I am talking about with CAD. So basically for CAD, the input is a set of polynomials. I'm talking about sort of classic CAD and not the sort of the many clever improvements that have come since. But you start with a set of polynomials in a variable ordering, and it has a very simple control flow. You go through this stage called projection, then this stage called lifting. In projection, you expand the set of polynomials A that you started with to something bigger, but something that has some nice properties that are going to help you later. And then you go to this lifting process, which is basically just a bunch of real root isolations, right? You isolate real roots of some of the polynomials in this set P, and then you substitute the roots that you've got into other polynomials and do more root isolation, and you do that over and over again. And when you're done with this process, what you get is highly structured, right? You get a decomposition of n-dimensional space into cells. The cells have to be cylindrical, if Jasper will allow me to use that word. And they need to be cylindrically arranged with respect to one another, right? Which means they're stacked on top of one another, basically, or they're not, they are in different stacks. And each element of P has to be sign invariant in each cell, and for each cell, we actually have a concrete sample point, so highly structured. So that's CAD from 40,000 feet. So now what's wrong with CAD? So I'm going to show this with an example, right? So this is an input where we have 6 polynomials. They're randomly generated to be almost but not quite linear, so they are all nonlinear. And these constraints, by the way, are all strict, which allows some optimizations in CAD, that's open CAD. So I'm going to be using those optimizations even. And what happens if we try the traditional CAD construction process here, using the optimizations that we have for open CAD? Well, first you project, and from our 6 polynomials and 4 variables that are all almost linear, that are quadratic at most, we end up with over 2,000 polynomials in our projection set. The degrees are as high as 28. So things really blow up. And then we go through lifting, which I couldn't finish with the setup that I had. But even if we're only creating these open cells, we still get almost 2,000 open cells in one-dimensional space that lift up to over 100,000 open cells in 2-dimensional space and so on. So I think it would be very conservative to say we would have ended up with over 1 million open cells from this small problem. Excuse me. So what about the three algorithms that I'm looking at? Well, you can solve this problem by hand. It's unsatisfiable, by the way, so you can't get lucky in a sense, right? You really have to go through all this work, but all three can be done by hand. Now, of course, I don't mean that you're isolating roots and computing resultants by hand, right? You're using tools to do those things, but the control, you just trace through the control of this algorithm by hand. And I did it. For the way I did it by hand, Nlsat, I ended up with 8 cells created. For the cylindrical coverings, we have basically we have these coverings that cause us to sort of cascade to other intervals, and there are 31 of those and 15 cells from my open NUCAD implementation. So this problem is not difficult for any of those 3 methods, right? So that's what's wrong with CAD. It's just when we're talking about SAT solving, at least, it just is way too inefficient, and there are better alternatives, right? These are better alternatives. So what I want to do is I want to consider a simple example formula, and I want to step through the computation of the 3 different approaches to see how they differ from one another, and maybe come up with some thoughts then on these algorithms at the end. So this is a simple formula with 3 strict inequalities in 3 variables. We have a cylinder from the first, we have a hyperboloid from the second, and the third is just the restriction that y has to be above a certain threshold. Now, this formula also contains only strict inequalities, which, as I said, allows this open CAD optimization, which is also an optimization we can do with NUCAD. And I don't know if this has been observed or not, but you have essentially the same optimization for both Nlsat and cylindrical algebraic coverings. All right. In the context of those things, the optimization is going to be that you're trying to cover a line with intervals. And the optimization is that you don't need to worry about the interval endpoints. They will not affect, you can ignore them, and it will not affect whether or not you find a satisfying assignment. All right. So that means that also for the rest of my examples, I don't need to worry about points, which is convenient. All right. So I'll make the same optimization for all of these methods. All right. So we're going to start with Nlsat. So Nlsat tries to build a solution variable by variable, checking against the formula F as we go. And the basic data structure is this stack of variable assignments. Now, I'm simplifying Nlsat a little bit. But also we're only worried about conjunctions here of constraints, which basically makes this simplification, I think, okay. When an assignment cannot be extended to the next variable, then we use CAD theory to generalize that current conflicting partial assignment to a cell full of conflicting partial assignments that conflict in exactly the same way. And then the negation of that description of that cell gets added to F as a learned clause. All right. And then we backtrack by popping an assignment off the stack and just repeat, we continue. So what is this going to look like on our example? Well, we're going to use the variable ordering XYZ for everything, by the way. So you start off with the formula as you see on the top. On the bottom, we have an empty stack. And what we're going to do is we're going to make an assignment for X first. I'm going to choose X equals 0, seems reasonable. The formula doesn't help here. And then we substitute X equals 0 into the formula. All right, so that means we're looking at that line that you see there into the Y space. And now we need to push a binding for Y. When we do this substitution, we actually find that constraint in P3 becomes univariate. And so it rules out everything below a threshold. In other words, in order to satisfy P3, that sort of green line and everything below is all automatically ruled out. So we have to choose from outside of that range. We might choose Y equals 0. And now we're going to substitute X equals 0, Y equals 0 into the remainder of the formula. P1 and P2 now become univariate, so we can use root isolation to find out whether there are satisfying assignments or not. And they're not. It turns out that there is no point actually here at which P1 will be less than 0. So we're going to do one projection step on P1, and that gives us a set of polynomials. And what we want is we want a region that contains our point, X equals 0, Y equals 0, in which the polynomials, the result of this projection, have constant sign. And so what we do is we build a cylindrical cell around that point with respect to those polynomials. It turns out to be very simple in this case. All right, we just have a line and we're above a threshold. So that orange region, that's our first real cell that we construct. So now we pop the binding for Y, and we have to choose a new value for Y. And of course, we've now gotten more bad regions. So we have to choose from only this restricted space in the middle. We might choose Y equals -1 at that point. We substitute X equals 0, Y equals -1 into the formula. By the way, notice that the formula grew, right? Because we added the negated cell description for our cell. All right, so the formula is getting bigger. All right, so when we substitute and we try to do linear, or we try to do univariate root isolation on P1 and P2, we find that there are no satisfying assignments for Z, but P1 and P2 individually could be satisfied. So it's really the combination of those constraints that's the problem. So we have to project those two polynomials together. That gives us a new set of polynomials. Now we need a region in which contains the point 0, -1 here, in which those polynomials that result from the projection have constant sign. And so we construct a cell that defines such a region. It's going to look something like this blue cell right here. Crucially, the cells can overlap in Nlsat. So you'll notice that this blue cell is actually overlapping the green cell. So that overlap is allowed. You get this freedom. So now, let's see, we're supposed to pop and choose a new value for y, noting that we added the negated cell description to our formula now. So now if we substitute x = 0 into our formula, we have lots of clauses that only contain y's. They're univariate. We do root isolation and we discover that we've actually covered this line. Now, it's not strictly true because there's that one point where the blue and the orange regions butt up against one another, right? That's one point we still haven't tried. But as I said, we're going to do this open optimization that says we actually don't need to try that point. All right. So what we want to do is we want to now generalize x = 0 to a bad assignment, a whole cell worth of bad assignments for x. So what we do is we take all of the cells that contribute to this, all the regions, all the polynomials that contribute to this conflict, which are the green, the orange, and the blue, and we will project them onto x, and then find an interval around x = 0 in which all the polynomials from the projection have constant sign. There it is. All right, and now its description gets added, the negation of its description gets added to the formula. So now, by the way, I just want to point out that if you look at this strip above that interval we just added, it's exactly the region where we have sort of nice properties that these cells really cover the entire y line. So now we need to choose a new value for x, and of course it has to be outside our bad region, right? Because it has to avoid what's defined by the red cell there. So we might choose x = 1, right? Now, substitute x = 1. And here's where things are interesting for me, because now when we substitute x = 1 in this formula, we have all sorts of regions that are now not available to us. The whole green region, the blue region, the orange region, we never bother to choose from them, all right? Because we've already learned that they won't work. So our only choice is something in this small little sliver here. So we choose something like y = -2.25. We substitute x = 1, y = -2.25, and then we find ourselves a satisfying assignment. All right. So that's Nlsat. So that's an example of how it works, and I think it hits the main ideas that are important for the distinctions I want to draw your attention to. So now we move on to cylindrical algebraic coverings. So again, we have a stack, but instead of just every entry being a variable assignment, each entry is actually a variable assignment plus a list of bad intervals that have to be avoided. All right. When we find a conflict, we produce new bad intervals using CAD projection. And when the bad intervals for a variable cover the real line, then we choose a covering set of intervals and do projection, but only one step of projection to generalize to a bad interval for the variable that's the next level down on the stack, and we backtrack. All right, so let's see how that's going to work then on our example formula. So once again, first thing we have to do is find a value for y. We might as well choose, or x rather, we might as well choose x = 0 because we have no information about bad regions for x. All right, and then we substitute x = 0, and we're going to look basically on this line for a value of y. All right, so we want to assign a value for y. We don't know it yet, but we want to assign one. But we do already have a bad interval because substituting x = 0, the constraint P3 greater than 0 actually already defines a bad interval for y. So we already have one bad interval. You see it down there, and we have to choose from outside that bad interval. So we'll choose 0 again, right? Because that's a sensible thing to choose. And then we will substitute x = 0, y = 0 into the formula. We'll find out that, so everything's univariate in the formula now. We can use root isolation, and we find out that we can't satisfy this formula because P1 is never less than 0. So we project P1, we get some polynomials, and now we want to choose an interval that contains y = 0 here on this line, in which the elements of that projection, of that one projection step, have constant sign. And that's going to give us this orange interval here. And so that gets added onto our list of bad intervals. All right. And then Well, we will have to choose a new value for y, and it'll have to be outside of our bad intervals. We'll probably choose something like -1. Substitute, find out that P1 and P2 can't be satisfied together. There's no value of z that satisfies them both, so we have to project. We project the two of those one step, and then that gives us a set of polynomials. Now we need an interval that contains y equals -1, in which all the elements of that projection have constant sign. That would give us this blue interval here. And notice once again that we actually do have overlap rather. I hope that shows up on your screens, but the blue and the green intervals do overlap, and that's allowed, and that's actually a feature of this algorithm. All right. So now we need to come up with a new value for y that avoids all of our bad intervals, but we can't. All right. So technically there is that one point at about -0.84. All right, we haven't tried that yet, and they butt up against, these intervals butt up against one another. They don't overlap there. But as I said, we're going to use this open optimization that says that we can just ignore it because all the inequalities are strict. So we would like to get a bad interval around x equals 0 now, right? So what we're going to do is we actually keep track of, it's not shown here, but we keep track of which polynomials define the green, the blue, and the orange intervals. And then we do one projection step with them, and that's going to define this interval, the interval that contains 0, in which all the elements of that projection have constant sign. All right, and that's going to be our bad interval for x. Now, before I go on, one thing I think is really sort of important to understand is that although you don't see any cells explicitly in cylindrical algebraic coverings, they're absolutely there. All right, they just get built incrementally. So hopefully these colors aren't too washed out for you to see. But if you look above that interval, the polynomials that define the green, the blue, and the orange regions are generalized, all right? And they actually give you cells. And so even though we don't keep track of them, these cells that come from the intervals generalized across the interval we got by projection, right? These are the cells that you build with cylindrical algebraic coverings, all right? So they're there, they're just not explicitly stored. All right, at any rate, this gives us a bad interval now for x. We want to choose a new value for x. We have to choose it from outside the bad interval. So where we choose perhaps x equals 1. We need a value for y. We notice already substituting x equals 1, we have this constraint here is univariate in y, so we get a bad interval out of it. We need to choose something outside of the bad interval. And here's where things really get different from Nlsat, right? Because we haven't remembered the full generalization. We haven't figured out the full generalization of the conflict we saw earlier. So we're going to have to relearn that 0 is not going to work for y. All right. And so we substitute x equals 1, y equals 0 into the formula, discover that there are no, oops, what did I do there? There are no z values that make P1 less than 0. So we're going to have to project P1. We get some polynomials. Now we need the interval that contains 0, in which those projection polynomials have constant sign. There it is. So we add that interval, all right? So we're going to have to choose again, and we're going to have to choose from outside that interval. So we choose something like perhaps x equals -1. Once again, actually, we're going to find the same conflict that we in Nlsat would have generalized to this region, all right? And we wouldn't have had to find it again, but we are going to have to find it again now. So we substitute, constraints of P1 and P2 become univariate in Z. We do root isolation, discover they cannot be simultaneously satisfied, which means that we project, we get some polynomials. Now we need to find the interval that contains -1, in which all the polynomials from that projection have constant sign. And so that's what that looks like. All right. So this is actually still part of what would have been that blue cell in the Nlsat case. So then we need to find a new binding for y. Now there's that gap there that we haven't sampled yet. So we'll choose a point from there like -2.25. And we substitute into the formula, do our root isolation, and find our solution. All right. So that's cylindrical algebraic coverings. So finally, we'll talk about NUCAD. And with NUCAD, we keep a priority queue of cells that we sort of haven't looked at yet. They have unknown status with respect to this formula F. And we dequeue a cell, and if F is not satisfied at that cell's sample point, then what we're going to do is we're going to use projection to split that cell into pieces. And the piece that inherits the sample point from the F that we had, or the cell C that we had chosen, F is going to be false throughout that cell, so we can ignore it. And then the other cells that result from this splitting process have to be enqueued again, so that are enqueued so that we might consider them later. Okay. All right. So what is that going to look like on our problem? Well, we're going to start off with a cell that consists of the entire two-dimensional space. By the way, I'm adapting NUCAD so that it follows the same procedure that Nlsat and cylindrical algebraic coverings are doing, where we're always basically working one level lower than the true number of variables in the problem. All right, so we'll substitute that 0.00 into the formula, do real root isolation, discover that P1 is not less than 0 anywhere over this point. So we'll split based on the projection of P1, and that'll split that one cell into two pieces. All right, the piece that inherits that 0, 0, well, we ignore that because the formula is false throughout it. The other piece that's not been colored in yet, that's got unknown status, so it gets NQ'd. So that will be the next thing we DQ. And we'll go ahead and try sample point 0, -1. We'll find out that P1 and P2 cannot be simultaneously satisfied above that point. Therefore, we project them, and their projection will be used to split this cell, and it'll get split into 4 pieces. The blue piece that you see here inherited the sample point from its parent cell, so we know the formula is false throughout that cell, but now we have 3 cells that get NQ'd that have unknown status. So we'll choose the highest priority one for that might be 0, -3. So we will, substitute 0, -3 into the formula, and actually, without having to do any further root isolations for Z, we'll already see that we've violated the constraint on P3. And so therefore we'll split by that polynomial P3. Once again, we get this green cell, which is not, the formula is not satisfied anywhere, and we get 2 subcells that we're going to have to look at later. We choose the next, DQ the next cell, sample point 1, -3. We substitute and find the same thing, that P3 is violated and that we have to split again. All right, so this is actually sort of like cylindrical algebraic coverings, where we are having to split by the same constraints multiple times. All right, but that's just the way the algorithm works. So then finally, we're going to choose this sample point here from this sliver of a cell, and we will find our satisfying assignment above it. All right. So what can we take away from this? So first of all 3 of these approaches are conflict guided, and that's clearly crucial to their being able to do SAT solving so much better than CAD does. All right, because what we do is that allows us to be lazy about our projections. Right, we don't project polynomials unless we actually have a concrete instance where these polynomials are involved in a conflict. All right. They all do retain the concept of cylindrical cells from CAD, but they all relax the structural requirements of CAD. And these relaxations allow us to use fewer cells to cover the space, all right? But they do this differently. And I think that's where a lot of the sort of interesting things to observe are. So Nlsat allows basically free overlap amongst the cells that it's creating, okay? They don't have to be cylindrically arranged. And as a result, cells are basically unstructured. So you can sort them by level, but beyond that, they're unstructured. And you see that in the formula, right? They just get added as an unstructured collection of clauses in the formula. So the trade-off here is that we get to use few cells. They're bigger cells, so we don't need as many of them, but we have to follow this very complicated control mechanism that they have, which is basically sort of the SMT control. All right, so it becomes a complicated and certainly hard to understand in terms of analysis algorithm because of that. With cylindrical algebraic coverings, we have limited overlap. All right, so there is some form of overlap allowed. We saw those intervals overlap with one another. On the other hand, we do require cylindrical arrangement, not full cylindrical arrangement. It's a limited form, but it's still cylindrical arrangement. The cells are implicit, although once again, I note that we could recover the cells in cylindrical algebraic coverings with just some extra bookkeeping. All right, so they're really there. But the cells are also built incrementally, which is interesting, right? So in Nlsat, when you decide you're going to build a cell, you build a complete cell, you project all levels, right? But with cylindrical algebraic coverings, you basically don't complete the construction of any of the cells until you're more or less done with the algorithm. You've made it all the way down to the first level. The tree structure of CAD is basically inherited more or less by cylindrical algebraic coverings. If you look at the cells that are created, they're implicit, but if you look at the cells that are created, they actually end up having that same tree structure. So we have more cells in cylindrical algebraic coverings, and they're smaller, but we get this really simple and easy to understand depth first search control, all right, which is a real nice aspect of the algorithm, right? So it can be written down much more easily than any of these other algorithms. So it's very natural that way. So, but we're trade-off is we have more and smaller cells because we have this sort of simple structure, this this high amount of structure in the result that we get. And it gives us this simple control. Finally, there's NUCAD. No overlap is allowed in NUCAD, but they don't need to, the cells do not need to be cylindrically arranged. So it was basically a different set of trade-offs than what we got from cylindrical algebraic coverings. So once again, we have more and smaller cells compared to Nlsat, but we get, as a result, this simple divide and conquer control. All right, so it becomes an easier algorithm to understand. All right, so in conclusion for all this, I hope that running through some concrete examples like this is helps people to understand the differences and similarities of these approaches, and maybe inspires us to think about some different decisions that we could be making in terms of how we relax the constraints of CAD, and how we use that relaxation to put off work. All right, so for example, you could imagine trying to make a version of Nlsat that has the same lazy cell construction that cylindrical algebraic coverings has. Right, so if we follow the same control as cylindrical algebraic coverings, we could learn full cells just like Nlsat does, but we would only need them to be described up to the current level. So we could actually be lazy about all cell construction, sort of combine Nlsat and cylindrical algebraic coverings. All right, so we could try to combine some advantages and mitigate some disadvantages this way. Finally, there are some assumptions that are common to all these approaches that maybe we could think about weakening. All right, and those assumptions are that, first of all, they all share the fact that we have cylindrical algebraic cells as our basic unit of generalization. And they all share the same basic assumption that the variable order is something that is fixed and determined ahead of time. So these are some things that we might think about weakening to see if we can find further advantages. All right, so thank you very much for your attention.
All right, thank you for the nice talk, Chris. So we have about 3 minutes. If anyone has questions. Yes, Akshay.
Chris, could you go back to the slide where you showed the decomposition of the Nlsat? Yeah, that's the NUCAD one. Yeah. So earlier when you had mentioned about the curtains being detected, are you talking about when you detected 0, -1 and 0, 0?
Well, I mean, there were no curtains in this case. Yeah. But the idea is because you're starting with a sample point and then substituting, if there was a curtain, then you would curtain at the sample point, then, well, you'd have to deal with that curtain. If there wasn't a curtain at the sample point, then the projection can be something very much smaller that simply ensures there are no curtains when we generalize.
Okay. Okay, no worries. And so, sorry to intrude into your talk, but there's one point. We needed the coefficients for Lex-Least invariance as compared to sign invariance. That's why we needed the coefficients of the other constraints.
I see.
Sorry to introduce into your talk.
I appreciate the clarification. Thanks.
Yeah.
All right. Any further questions?
I don't have a question, but I do have a plea to Chris to write this up into a paper, because I think it's fascinating, and I was furiously trying to take notes, but I don't think I got all of it down. But exactly. I think it well deserves writing up, is what I'm saying.
I appreciate that. Yeah. I will say that it was tremendously instructive for me to go through by hand all 3 algorithms. I started with a much bigger example, actually, and went through them all by hand, and it was tremendously instructive for me. So I thought I'd try to share that.
Yeah. Chris, is it a coincidence that we always end up with the same point, same example, or is it the case that these 3 will actually follow a very similar route in general?
So it's certainly not a coincidence, because the example is small, so you're sort of limited. And because I made sure we always, when you make an arbitrary choice, I made sure we made the arbitrary choices that would allow us to end up at the same point. Because it makes the idea is for the comparison there.
Yeah.
So with all these methods, there are arbitrary choices you have to make that can greatly impact how the algorithms run. That's hugely true in the SAT case, because you could just arbitrarily guess the satisfying assignment. But even in the unsat case, you make these arbitrary decisions that are going to impact the path that your search takes. And that's true for all of these methods.